Okay, guys, welcome back. So, what we were doing yesterday was to try to solve the portfolio choice problem for this general diffusion model. And we started by deriving the Hamilton-Jacobi-Bellman equation for this model, and by seeing a few tricks that help us solve this Hamilton-Jacobi-Bellman equation. So, remember, just to recall the notation, we have this diffusion model where the interest rate is stochastic, the risk premium is stochastic, the volatilities are also stochastic, and the correlations between the asset returns and the state variables are also stochastic, and the state variables themselves are described by this autonomous diffusion. Okay? So this is a sort of framework, if you will, that summarizes close to 90% of the models you see in the literature, except the models with jumps, of course. And what we did yesterday was to arrive essentially at this equation, which is the main Hamilton-Jacobi-Bellman equation of this problem. And then we found a few ways to reduce the dimension and to also simplify a little bit the equation, in the sense that we were able to get rid of this term in the denominator that is highly nonlinear. And we reached to the point where, with certain parametric assumptions, we could have a feasible plan to solve the Hamilton-Jacobi equation, even with a finite horizon. Okay? So what we're doing today is to continue with the remaining tricks that I have to show you, and then we're going to look at how to actually implement a verification plan for this kind of equation, and how to further simplify it in the sense of focusing on the long run asymptotics, which means on the strategies that are optimal when there is still a long time to go before the horizon, so when you're young, like yourself. Okay, so what is the long run horizon limit? The idea is that you fix the time at which you are, and then you push the horizon to plus infinity. Okay? So you say, well, let's suppose that I have a 5-year horizon, what should I do? Well, now let's suppose I have a 10-year horizon, what should I do? Let's suppose I have a 30-year horizon, and the idea is that, if the model makes sense, then when the horizon is long enough, it shouldn't matter exactly how long it is. Okay? So if you have a 30-year horizon and 50-year horizon, the optimal portfolio should not change very much unless there is something a bit pathological in the model. Okay? Of course, this is not true in general. So you can construct the most bizarre counterexamples in which the portfolio diverges or oscillates as the horizon goes to plus infinity. But these examples are, rare beasts that you can find in a zoo, but that are not particularly relevant for applications. Okay? So in applications, typically you have state variables which oscillate over time, typically that they are ergodic. So if a state variable is ergodic, it means that when you have a very long horizon, you basically have absolutely no idea of what the state variable is going to be a long time from now. And so to the extent that certain decisions are based on what is going to happen a long time from now, these decisions should not be particularly dependent on the value of the state variable today. Okay? So that's more or less the philosophy. There's nothing rigorous here. It's just the starting point. So what we observe, and what we saw yesterday actually in the Samuelson model, is that after you factor in the dependence on the wealth, the value function typically increases geometrically with the horizon. Okay? So there are two reasons for this. One is that the growth of wealth, both coming from the risk-free rate and from the risky assets, tend to grow geometrically because you compound your investment. And the second is that we are using a power utility, and the power of an exponential is still an exponential. Okay? So in practice, we have seen that there is this kind of dependence. Now, for the Samuelson model, we knew exactly what this rate was. In general, we don't. Okay? In general, if we have a complicated model such as the one I introduced yesterday and I recalled 2 minutes ago, this is part of the problem that we want to solve. Okay? What is the rate of growth of our wealth as a function of the horizon? So we can think of this in a quite concrete way. We can think of this as a certainty equivalent rate. What does that mean? So suppose that now I give you the opportunity to live in the world where you are, okay? Or to switch to a different world in which there are no risky assets, but in which you have the opportunity to earn more than what you get in this particular world on the risk-free investment, okay? So suppose that I make you sign a piece of paper that I offer you the possibility to sign a piece of paper which says, well, I will never buy a risky asset in my whole life, okay? But in exchange for this agreement, I will take an interest rate which is 2% higher than what I get normally. Okay? Would you take this offer? Okay? So it depends. If it is 2%, it's not really clear. If I offer you 10% more, risk-free, well, maybe you're going to take it, right? So 5%, who knows? 1%, probably not. Okay? At any rate, it depends, of course, on your risk aversion. So if you are very, very risk averse, you would not touch risky assets anyway, so you're going to take a very low certainty equivalent rate anyway. If you are very risk tolerant, then you are not going to settle for 1% or 2%, you're going to ask for more. Okay? So this lambda should definitely depend on risk aversion. Now, what we know is that in a Samuelson market, so when you have constant investment opportunities, the value of lambda is exactly this. Okay? And we interpreted this yesterday already. So what we want to do here is to plug this guess. Okay? It is no more than a guess at this point for the value function, and to see what is happening in the Hamilton-Jacobi-Berman equation. Now, of course, we are not going to leave this as the only form of dependence. We are going to consider also the dependence on the state. So effectively, here I should have added lambda plus some function w of y, which is another typo. Okay? In any case, when you absorb the dependence of v on t in this guess, this is what the equation that you're getting. Okay? So this equation is the same as the equation we had here, with one difference, that now wt doesn't exist anymore, because we have guessed that w, as I wrote it here, is actually some w which only depends on y, plus some constant times t. So when we take the time derivative, what we obtain here is just this term that you see here as lambda. Okay? So what is the advantage of this approximation? Okay, so what is clear at this point is the disadvantage. The disadvantage is that once you cross this line, you have an equation which is not even the Hamilton-Jacobian equation of your original problem. Okay? So not only you have the problem to find the verification, you know that you cannot find any verification because this is another equation. Okay? Now, the advantage is also not hard to understand. It is that w now depends only on y. Okay? So we got rid of one more variable by tampering only with one term of the Hamilton-Jacobi equation. Okay? So if we can find any relation between the solution to this equation and the original optimization problem, then this is going to be more promising. Okay? Now, at this point, if you have a model which allows for a quadratic guess, you don't have to assume that the coefficients depend on time anymore. You can just take B to be a constant vector, A to be a constant matrix. You can plug this ansatz here, and you can see whether you can solve the equation, which becomes just a system of equations in B and A. Okay? And for many models, this actually works. As I mentioned yesterday, the models for which this works is typically when you have Ornstein-Uhlenbeck state variables and linear drifts and possibly constant volatilities. Okay, that's a case in which it certainly works. Sometimes it works also if you have quadratic drifts. Okay, now let me show you an example at work where we can actually solve the Lagrange problem and we get a constant solution. So we're going to take this simple stochastic volatility model in which we have two sources of noise. One is the Brownian motion that drives the asset, and the other is the Brownian motion that drives the state. The state, Y, controls two things. One is the squared volatility, and the other is the risk premium. So we consider this model, which allows for time-varying risk premium, and we see how this is going to fit into the framework that I have discussed so far. So the Jacobi-Brownian equation looks like this. Here, Y is a scalar, so we have a single state variable. So after we got rid of the dependence on wealth and on time, now this is just an ordinary differential equation, okay? And it is a nonlinear ordinary differential equation because of this term, but otherwise it is not particularly scary. So what we do here is to try a very simple guess. We take a linear guess, okay? We assume that W is going to be equal to some beta, which is a number we have to find, times Y, okay? It's almost embarrassing, but in fact it works, okay? So if you take this, you're going to get two equations, because here you will get two terms when you plug this. One term is constant, the other term is linear in Y. So if this has to be equal to 0, both the constant term and the linear term have to be 0, which means that we have two equations. These are algebraic equations in the parameters only. And if we have two equations, we better have two unknowns. In fact, we have the unknown beta, which we started from, and the other unknown is lambda. Okay? So remember that we want to find the growth rate for the certainty equivalent. Okay, so this is not particularly difficult to solve. This is a quadratic in beta, and it does involve lambda, so we're going to solve this one first. We're going to plug the solution here, and then we find lambda. Okay, so this is not particularly challenging, and the solution that we get here is this. Okay, I'm not going to write beta explicitly because it's just a bit messy, but what we want to do now is to interpret this formula. Okay, so the first part, this is just the Merton portfolio, mu over gamma sigma squared. Okay, this is the portfolio we would use if we thought that the current value of the risk premium were here to stay. Okay, the second part is the intertemporal hedging, and we want to understand a little bit more about this. Now, notice first that this is a model in which the optimal portfolio as a proportion of wealth in the risky asset is constant. But this is not a model in which the investment opportunities are constant. Okay? So if you were wondering whether a constant portfolio implies constant investment opportunities, the answer is no. If you have constant investment opportunities, you get a constant portfolio, but that's just one case. You can get a constant portfolio without having constant investment opportunities, and this is the example. Okay? Now, the second piece, so in particular, if you think of this as a model for allocation in equities, Here, this is telling you that you should hold a proportion of wealth in equities which is not necessarily equal to mu over gamma sigma squared. It may be different. Different by how much? Well, it depends. So, it is not going to be different, for example, when rho is equal to 0. So, if the correlation between the two shocks is 0, or if epsilon is equal to 0. Epsilon equal to 0, epsilon is the volatility of volatility. So, this is effectively the case where the risk premium is constant. Okay? So, these are two trivial cases. Now, it is going to be 0 also if beta is equal to 0. Now, let's see when beta is equal to 0. To see when beta is equal to 0, we're going to look at this equation. We're going to plug beta equals 0, and we see when this works. Okay? So if we plug beta equals 0, you get this goes away, even the image goes away, this goes away, and so this has to be 0 for beta to work. When is this 0? Well, nu cannot be 0, otherwise it means there is no risk premium. Well, gamma has to be 1. Okay? So you see that the only guy who doesn't want to intertemporally hedge is logarithmic utility guy who does not really care about time-varying investment opportunities. For him, every day is the last one, so he just pretends that the current value is the only value. Okay? Everybody else is going to care. Okay. Now, let me show you one more trick to solve these equations, and this trick will work under two conditions. One is that you have a single state variable, and two is that the correlation between the state variable and the entire set of assets is a constant, in the sense that rho prime rho, the sum of the squared correlation, this is a constant. Each correlation can vary, but the sum of the squares should be a constant. So then you can use this interesting transformation of power type. You set V equal to U to the delta, and then you determine the only value of delta which makes the nonlinear term go away. Okay? When it is this term. If you're doing this, now you have, this is the only case essentially, in which you have a linear equation, actually, for the Hamilton-Jacobi-Bellman equation. Okay? And this is a privilege that generally you have to forget about, because the Hamilton-Jacobi-Bellman equation is highly nonlinear. If you have this linear equation, you can also try to write the solution in terms of a Feynman-Katz expression, such as this one. And then if you have a way to calculate this easily, either explicitly or with some other numerical method, this is another tool that you can employ. Okay? And under this probability, which essentially is an equivalent probability to P but doesn't have any particular interpretation, you have changed the drift of the state variable by adding to the drift that it normally has under PB this extra drift. Okay? And this is the probability under which you have the Feynman-Katz representation. So this is not the original probability E. Okay. Now, another important application of this technique is pricing. Okay? One of the questions that people typically wonder about is how should I price a certain payoff or a certain dividend stream or anything in between in an incomplete market. Okay? Which martingale measure should I pick? Which stochastic discount factor should I pick? Okay? And of course, there must be a link between your attitude towards risk and the martingale measure that you're going to pick. So in general, when you are solving a portfolio choice problem, even if you don't want to solve a pricing problem, you have solved it anyway. Okay? Because there is a one-to-one correspondence between the marginal utility of the optimal payoff and the stochastic discount factor. They have to be proportional. So if you give me one, I give you the other. So if you have the optimal portfolio, which has this expression, okay? So if you have been able to find the value function little v, and therefore you have found the optimal portfolio, what you can do is to look at the marginal utility of the wealth of this optimal payoff. So you can look at what is the implied stochastic scan factor, and it is going to have this expression. Okay? So with this expression, you see that in this integral, you still have the same term that you see in the optimal portfolio. Okay? Which tells you what is the value of eta that you have to plug in this general expression for the stochastic scan factor. Okay? So if you have solved the portfolio choice problem, you can find immediately what is the martingale measure that you have to pick. And once you have the change of measure between the original measure and the risk-neutral measure, you can use Gaussian theorem to write directly the asset price in the risk-neutral measure implied by this stochastic scan factor. Okay? And it looks like this. Now, if you look at the return, you see that the return, the excess return actually, process clearly has drift 0. It must be, because otherwise this is not a risk-neutral measure. Okay? The excess return has drift 0 under the risk-neutral measure. So mu is gone, as it should. The interesting part is what is happening to the drift of the state variable. This is the only thing that can change, because the diffusion coefficients have to stay what they were, otherwise the two measures are not equivalent. The drift of the excess return process has to become 0, so the only thing that can do something, a bit unpredictable is the drift of the state variable. Okay? And this is where martingale measures of different type will differ. So what is happening here is that we have an extra term which does not really depend on the value function. So here you see that this is just the covariance between the states and the assets. This is the covariance matrix of the assets, and this is just the risk premium. So this term is fixed for all martingale measures. It is like a hedging term which accounts for the correlation between the states and the assets. What is really changing is this term. Okay? Now, you should recognize this factor here. This is the quantity that becomes 0 when the market is complete. Okay? So if I have a complete market, this becomes 0 and the value of eta doesn't matter anymore. Why? Because in a complete market there is just one martingale measure, and that is the martingale measure that you obtain by just adjusting for the correlation of the between W and Z. Okay? The solution to the portfolio choice problem does not affect the optimal martingale measure when you are in a complete market, because in a complete market there's just one martingale measure. Okay? So in a complete market to price, you do not need to solve the portfolio choice problem. If you want, you can solve it, but you can price anyway because there's just one martingale measure. Okay? In general, however, you have to. So if this, for example, if you're in a fully incomplete market, then this will be 0. Okay? And eta does matter. And anytime that this is non-zero, eta still does matter. So what you're getting is that this term that you see here, Vy over V, controls both the intertemporal hedging demand of your portfolio and also the drift of your state variables under the corresponding martingale measure. And it also has to be clear that if you have a certain risk aversion, then you have to, if you invest according to a certain portfolio, you must also price according to this measure. You cannot choose another measure and then invest according to the portfolio that doesn't correspond to that measure. Okay? Otherwise, you're going to fool yourself. When you price under a certain measure, you are pricing in such a way that you are indifferent between buying or selling a small quantity of the payoff that you have just priced, okay? That is the only way of pricing rationally with respect to a certain utility function, okay? If you price according to another martingale measure, but then you invest according to the one implied by this portfolio, then you're going to come up with a price at which either you want to buy or you want to sell. Okay? So you are selling yourself stuff. Okay? And why are you buying it? Because you priced it incorrectly. Okay? Even for yourself. Okay. So I hope that this makes clear what is the relation between the optimal investment problem and pricing problem in incomplete markets. They are exactly the same problem. If you solve one, you can solve the other. If you give me the optimal martingale measures, I can tell you what is your optimal portfolio, because you are telling me from the drift of the state variable what your optimal portfolio should be in terms of intertemporal hedging. Okay, so what we're going to do now is to show how to make this rigorous. Okay, so if you have found an explicit solution to the long run Hamilton-Jacobi-Bellman equation, how do you close the deal? How do you show that this is actually optimal in any sense? Okay? So in order to do this, we need to give a couple of definitions, and we are going to make some technical assumptions which guarantee that the steps we are going to make are actually logically sound. So, first of all, it should be clear that the reason why we want long-run solution rather than finite horizon solution is that, generally speaking, they are much cleaner. Okay? You do not have some crazy dependence on the horizon, which muddles the formula. You have much more simple expressions, which are also easier to interpret, as I showed you from the previous example with stochastic risk premium. Okay, so we're going to look at a long-run verification theorem. So the first step is to find a solution to the Hamilton-Jacobi-Bellman equation. The way we find this is basically with a bunch of tricks. Okay. Then the second step is going to find some duality bounds, and for the purpose of applications, this is actually all you care. Okay. The third part is interesting theoretically because it allows you to say that in the long run this is actually going to work, but this is not going to tell you how long the run has to be for this to be practical. Okay? So if it works in 200 years, maybe it's not so useful, but if it works in 20 years, then it's useful. And this will tell you if it works in 20 years. Okay? This will not. Okay, so first assumption is that all the coefficients we have, the interest rate, the drift of the state variable, the risk premium, etc., they are all smooth enough. What we ask is that essentially the drifts are C1 alpha and or C1 gamma. Well, I shouldn't call it gamma because gamma is really the risk aversion. So this is not the risk aversion, okay, it's some other exponent. And the covariance matrices are all C2 alpha. Now, just for notational reason, I'm going to look to call the inverse of sigma bar, otherwise the formulas are not going to fit, okay? There's not a deeper reason for that. Now, first assumption we have to make is that the model we write actually makes sense, okay? The way that this can be written properly is that we say that we want a unique solution to the martingale problem implied by the equations we have written already, which is basically D plus K dimensional diffusions. The first D components come from the assets, the next K components come from the state. Okay? So this is a D plus K times D plus K covariance matrix and a D plus K drift, and from this we obtain operator, and this operator identifies a certain martingale problem. For this martingale problem, which is essentially equivalent to canonical version, so a version of the canonical space of a weak solution to this stochastic differential equation, we want a global solution, okay? So what is a global solution? We want two things. So first of all, we are going to consider a certain open set E, which is where the D plus K dimensional, sorry. So first of all, this should not be N, should be D, okay? Because it's a number of assets. And this should be some open set E. So we want our solution to live on RD times E. So the excess returns live on RD, okay? There isn't any much more interesting open set for that. So we're going to settle on RD. The state variable can live in other places because, for example, if you have an Austin-Uhlenbeck process, then it lives on R. If you have a Cox-Ingersoll-Ross diffusion, it will live on 0 plus infinity. If you have some Jacobi process, it will live on 0, 1, maybe, open. So you want to be a little more flexible there. And what we want is that the probability under Px that x0 starts at x is 1, okay? This is just saying that x begins at 1. We want that xt lives in Rn or Rd times E with probability 1 at all times, so it must not get out of Rn Rd plus E. So in particular, it should not hit the boundaries, okay? So if you have a Cox-Ingersoll-Ross that touches 0, that's not okay. And at that point, you also want that if you take any bounded smooth function of the state, when you subtract the drift that comes from the operator, then this should be a martingale, okay? So this is the definition of a martingale problem given by Struck and Verhaden, and it is a canonical version of a weak solution to the SDE. This is not something for which there is a recipe, okay? There are recipes, but usually don't work in interesting examples because, for example, for Cox-Ingersoll-Ross, you will not have the Lipschitz property near 0, so you can forget about general theorems. But in general, all that this slide is saying is that once you write down a model, it is your responsibility to check that the model continues to live in the set that you have specified and it doesn't hit the boundary. Okay? That's all. So we give the following definition for Lagrange optimality. So we call a portfolio pi Lagrange optimal. So portfolio pi describes an abysmal strategy if it satisfies the following property, that it achieves the maximum rate of growth, okay, for the certainty equivalent. So if you look at this quantity, the power of the expectation, this is just the certainty equivalent in monetary term of this particular payoff x pi t. So we're not going to take the limit of this certainty equivalent because we know it will certainly go to 0 as the horizon goes to plus infinity, because if I give you 200 years to invest, you will make a great amount of money. If I give you 1,000 years, you will make even more money, and so on. So we do not expect this to converge anywhere. If we take the log, we also do not expect that to converge because we expect that, in fact, to increase linearly. So we're going to divide by the horizon, and this is something that we expect to converge, okay? So if you can achieve the maximum rate possible, then we're going to say that this portfolio is Lagrange optimal, okay? So this is one way to define rigorously a notion of Lagrange optimality for a portfolio. For the risk premia eta, we're going to give a similar dual definition. We're going to say that they are Lagrange optimal if the same rate of growth of the dual problem is also as low as possible, okay? Now, the interpretation of this is less clear. What does it mean to have low rate of growth for the moment of a certain stochastic discount factor. It doesn't have an obvious interpretation. But if you look at the duality bound that we did 2 days ago, then you see what is the relation. The duality bound for power utility tells you that the certainty equivalent of any PROF is always less than or equal than the power of a moment of the stochastic discount factor for any stochastic discount factor. So you can pick any x here, you can pick any m here, the inequality is always true, which means that here you can take the sup over x, here you can take the inf over m, and the inequality is still true. So what we expect is that if we find a portfolio pi which achieves the highest rate of growth, and we find a risk premium eta which gives us a stochastic discount factor which achieves the lowest rate of growth, then these two growths should probably be the same. And in fact, we define a pair, pi eta, to be long run optimal if each of them is long run optimal and the limits are the same. Okay? So, the idea here is that if you want to solve the optimal portfolio problem, it may not be so easy. If you want to solve the optimal risk premium problem, may also not be so easy. But if you want to solve them both, actually it can become easier. Okay? Because if you find a portfolio which achieves a certain rate of growth, and you find another risk premium which achieves the same rate of growth, you don't know whether either of them is optimal. Well, if they achieve the same rate of growth, they are optimal, both of them. Okay? Because this rate of growth must always be less than or equal than this rate of growth. And so when you find them to be the same, both of them are optimal. So philosophically, it's like thinking of portfolios as fishes which live under the sea, as risk premia are birds that live in the air, and if you find a fish that is touching a bird, you know that the fish is above all the other fishes and the bird is below all the other birds. Okay? It is exactly the same story. So, what we're doing here next is to assume that we have solved the HJB equation. Okay? Which HJB equation? The ergodic version, the one without the t dependence. Okay? And this is the one in which you find the value lambda. Okay, where is the value lambda? Here. So what does it mean to solve this equation? It means that you have found two things. One is lambda, the other is w. Okay, so a solution to this means a solution for w, which is the function in the equation, and lambda, which is some arbitrary parameter. So the problem with doing this is that in general, if you fix a lambda, you will find some solution w. So you have to find a way to pick the right lambda somehow. Okay? So when you are working with applications, you see that sometimes there is some natural lambda to look at. But if you're just looking at this equation, a priori it is not clear which lambda you should pick. But when you think of what is going on here, it is actually clear which lambda you should pick. You should pick the lowest possible lambda. Okay? Because here we want always to maximize. Okay. So notice that this equation becomes nearly trivial when you're working with logarithmic utility. Okay? Logarithmic utility corresponds to gamma equal 1. If you take gamma equal 1, the nonlinear term disappears, because here you have, no, sorry, the nonlinear term does not disappear here. But, yeah, it disappears because there is a gamma also here. Yeah, it does disappear. And also this term simplifies even more. So at the end of the day, it's quite linear, okay? Which reflects the fact that logarithmic utility is infinitely easier than any other value of gamma for the portfolio choice problem. Okay, now The next assumption you need to do, so the extra burden on the user of this theorem is the following. You have to check that after you have solved the HJB equation, now you write another SDE. This is an SDE in which you have changed the drift of the assets and also the drift of the states. Okay? So in particular, this is not an SDE under a risk-neutral measure because this drift is not zero. Okay? I will tell you the interpretation shortly. But what you have to do to use this kind of result is that you need to write this SDE and check that this also has a unique solution to the martingale problem. So in other words, after you have solved your HJB equation and you write this new dynamics, the state variable should not leave its set, okay, and should not explode either, okay, or the assets as well. So this dynamic should still make sense. If you make sure that this is indeed the case, what you achieve is that now you have a license to change the measure between P, which is the original measure, and P hat, which is the measure defined by this martingale problem. And you will know that these two are equivalent measures. In fact, you can see that the two diffusion coefficients are the same, okay? And there's a theorem that tells you that if you have the solution between the two martingale problems and the diffusions are the same, then you can check the two measures are equivalent, okay? So that's the idea. Now, let's go to the interpretation of this, okay? In particular, let's look at what would be the optimal portfolio for a logarithmic investor who lives in a world where this is the true probability measure. So if you're a logarithmic investor, your optimal portfolio is always mu, which is what we have here, divided by sigma squared, which is this, okay? Divided by sigma squared really means sigma inverse times this, okay? And what is the expression that we get? Well, we get the same exact expression as the expression that we get for the optimal portfolio, not for the logarithmic investor, for the gamma investor, but not under this probability, under the original probability. So we call this the myopic measure because this is the hypothetical physical measure under which the optimal strategy for a myopic investor, so a logarithmic investor, coincides with the true optimal strategy under the original measure for the original investor, okay? So in other words, if you have power utility and live under P, or if you have logarithmic utility and live under P hat, you make the same exact decision, okay? Now, the finite horizon bounds, which are the most useful part from an application point of view of this theory, are the following, okay? The optimal portfolio is given by this expression. The optimal risk premium is given by this other expression. And, well, we do not yet know that they are optimal, okay? So the candidates, portfolio and risk premium, are given by this expression, and these two candidates satisfy these bounds, okay? So what are these bounds saying? Well, this is essentially the certainty equivalent of this payoff, okay? At a fixed horizon. And it is telling us that the certainty equivalent of this payoff is equal to the exponential of the certainty equivalent rate times t. So you see that there is a reason to call this certainty equivalent rate because it is the rate at which the certainty equivalent of the payoff is growing, okay? Plus some transitory term, which depends on the state, and the state typically oscillates, okay, times some error term, okay? This error term is the expectation under p hat, not under p, of some exponential of the state variable at the horizon that we're talking about, okay? Raised to a certain power, okay? If we look at the dual utility for the corresponding stochastic discount factor, we get the same exact expression plus times a different error term, okay? So what's the idea? The idea is that we know that this is always less than or equal than this. This is the duality bound, okay? Now, if we can show that this dies off as a rate, and this also dies off as a rate, then we get the optimality, okay? That's the idea, from a theoretical point of view. From an application point of view, these two are even better, because if you tell me that your horizon is 10 years, I can calculate this directly. I can probably get an idea of what this is using some model-specific estimate, or if it comes to really doing this numerically, you can use a Monte Carlo simulation, because this is just an expectation. Okay? And then you can tell me how far apart this is from this, and by looking at the ratio between this and this. By taking the log of the ratio divided by t, you can even calculate how many basis points you are losing by taking the long-run solution rather than the finite horizon solution, which would solve the hypothetical HJB equation with the time-dependent term. Okay? So you can really relate what is happening to the original optimization problem with what is happening to the solution of this long horizon problem. Okay. So how do we get the long horizon solution? This is the summary. First, you have to solve the HJB equation. And for different lambdas, you get different W's. So you try to find the W that corresponds to the lowest lambda. Then you have to check that the myopia probability is well defined, okay? And this is done after you have found W and lambda. At this point, you can find the finite horizon bounds, and they tell you how good the long-run solution is. And to check the theoretical optimality, all you have to check is that the growth rate of the error terms in the primal and the dual problems are both 0, okay? And this is typically done with some, well, we have a theorem for that, and one can see whether the theorem applies. Even if the theorem does not apply, it doesn't really matter. You can try to do some estimate for the W that you have found and the Y that you have found, but, you know, practically, Y will be some ergodic process, okay? So when T is large, this will have a long-run distribution. So the only problem is whether W raised to this exponential is making the distribution of Y having tails that are too fat, so that this expectation blows up, okay? But in many cases, it doesn't. Okay, so let me show you quickly the proof of the first, the finite horizon bound. I will not spend a lot of time on this, but I want to show you just because it's really easy once you do it properly. So the idea is that to prove this, we're actually going to prove something even more. We're going to prove that not just the expectation of this is equal to the expectation of that, but that this, after we get rid of the exponents and we look at the portfolio itself, the portfolio itself is equal to this times that multiplied by dp hat over dp, okay? And then we are going to pass to the expectations, and the expectation is going to give us this directly. So, first of all, what is dp hat over dp? Well, this is just the stochastic scan factor, okay? Normal modulo the interest rate, which you have to multiply by. And it is given explicitly by this expression, okay? So all I've done here is to plug the value of eta that was coming from the dual problem, okay? So to check that the bound is true, all we have to do is to check that x to this power is equal to the exponential of lambda t plus wy, which is the initial value of y, minus w of yt, times dp hat over dp, which I'm calling here big dt, okay? If I prove this, then I can pass to the expectation and I get exactly the finite horizon bound. Now, this is going to be practically a mechanical matter, because to check this, we can just pass to the logs, okay? When we go to the logs, we get this expression. Now, the logs are convenient because this is a stochastic exponential. So if you plug it on the right-hand side, here you're getting just m minus the quadratic variation of m divided by 2. And also x is going to be a stochastic exponential, so we can just plug the log of x, which is equal by, given by this expression, okay? So we plug this here, we plug the value of pi that comes from the candidate, okay? And we get this insane expression that, however, is relatively, straightforward. Likewise, for the right-hand side, we plug the expression that comes from the optimal dual bound, and we get this other insane expression, okay? When we take the difference, we see that a few things die out, in particular, this piece and this piece that you cannot see properly because there should be a dBB. They are exactly the same, so they die out. And all you're left with is this big drift and this stochastic integral with respect to the gradient of W. Now, when you see this, this is basically screaming for an Ito's formula to be used. And in fact, that's what you do. You use Ito's formula, of course, with W of y. If you use Ito's formula with W of y, you see that it gives you exactly the term you have here, plus these two remainders, okay? So these are two drifts, and you're going to put it with the other drift, and this is the transitory term that appears in the bound. When you look at what you have accumulated within all the drift terms, these two terms plus these other two terms, all these other terms, that's just the HJB equation. So you know that this stuff is equal to lambda, okay? And that gives you precisely the bound that you want, okay? So this is the wealth bound, so the primal bound. If you want to do the dual bound, you do exactly the same story, okay? You plug everything, and I'm not going to go in detail, but it will give you exactly with the same procedure the bound that I wrote earlier. So this is actually quite easy, and it gives you a strategy to solve these portfolio choice problems with stochastic investment opportunities, even when you do not have a simple or even a solution at all for a finite horizon. But when you look at a longer horizon, you can find relatively simple solutions, and that are usually also more informative from an economic point of view of what is happening in the model. Okay? All right. So at this point, I'm going to end this topic, and I want to show you some related problem of portfolio choice that you can solve with similar techniques, not applying directly what I showed you here, but by applying some variation of it. And this has to do with one of my favorite topics, which is market frictions, okay? Market frictions, in this case, I'm talking about transaction costs. And to be even more precise, I'm talking about proportional constant transaction cost, which means what is happening when you have two prices for buying and selling. We're going to call S the price at which you buy and the price at which you sell. By Murphy's law is lower, so we're going to call it 1 minus epsilon times S. Okay? For the sake of simplicity, we're going to consider the simplest possible model, which is geometric boundary motion. So we're going to have some constant interest rate, some constant risk premium, and some constant volatility. Okay? So the novelty here is that we have two prices. That's the only novelty. Otherwise, we would be talking about the Merton problem that we discussed on the first day. All right. We still work with power utility because we want to have something that compares with what we know already. And now we're going to use the certainty equivalent rate as an objective. So we want to solve the problem for a long horizon. The reason why we want a long horizon in this setting is that the transaction cost generates some dependence on the boundary, which is interpreted as follows. Suppose that you have 10 years to go. You don't care about what happens at the end when you have to liquidate. You do whatever you need to do for the portfolio. But suppose that now you have 6 months to go. And theoretically, the model would tell you that you have to rebalance your portfolio to, let's say, 50-50 between stocks and risk-free assets. Well, are you going to do it? Well, maybe not, because you will have to liquidate everything in 6 months from now anyway. So it's not really worth it to spend money in rebalancing when the rebalancing is not going to last much anyway. It's going to be pointless, okay? So because of these considerations, when you have transaction cost, you have a distraction, which is the dependence on the horizon, which is like a boundary effect when you talk about physics and you're studying some electric field within a cylinder, and you know that you don't care about what happens near the boundary, you just want to know what is happening inside, okay? So what you assume is that your cylinder is really long, okay? And then you forget about the boundaries, okay? So this is the same exact story, but with the horizon for the investment. We don't care about what is going to happen 6 months or 1 month before the horizon. We want to know what should happen before. So we push the horizon to plus infinity, and we look at the quantity that we know should converge, because we know already the solution to the Merton problem, and that should be the rate of growth of the certainty equivalent of the optimal portfolio. Okay? So this model, in a slightly different presentation, was introduced by Dumas and Luciano, and we're going to give a similar solution somehow. Now, the first question that one needs to settle when working with transaction costs is what is the right set of strategies, okay? We discussed on the very first day that when you do not have any sort of friction, then all you need to ask for trading strategy is that it doesn't generate doubling schemes, okay? And that it is integrable with respect to the asset price. Now here you have to be a little more careful, because you need to also make sure that the strategy does not generate infinite trading costs in a finite time. So what are the trading costs depending upon? Well, they depend on the variation of the number of shares on the entire interval. And if you want to generate a finite amount of trading costs, you must have a finite variation strategy. So what we do is to describe by phi t the number of shares that you hold at time t in the risky assets. Okay? we can write phi t as the difference between phi t increasing and phi t decreasing, where phi t increasing represents the cumulative number of shares that you have bought. So how many shares you have bought since the beginning of your trading strategy. And phi t decreasing is the number of shares that you have sold since the beginning of your strategy. The difference is the number of shares that you hold time t. Okay? Because you write this as a difference of two increasing functions, then you are guaranteed that this is a finite variation strategy. Okay? Once you describe the number of shares in the risky asset, the number of units in the risk-free asset is automatically determined by the self-financing condition, which, when you have two prices, looks like this. Because when you buy, your cash goes down by the ask price. Okay? The ask price is the higher price at which you buy. And when you sell, your cash goes up, but only by the bid price. Okay? Because that's the price at which you sell. So when you rewrite the self-financing condition for the cash, these are the number of euros in cash, and these are the number of euros in the stock, you get these two equations, okay? And these two equations are telling you that the drift is the same as in Merton, the diffusion is also the same as in Merton. What is changing here is the price at which you accumulate shares, which is conventionally taken to be the ask. This is just a convention. You could take the bid and the problem would have the same solution. It doesn't really matter at which price you value your risky position. When you have to liquidate it, you will have to use the bid, but it does not affect the growth rate anyway. Okay? And the cash, instead, must be treated separately for the ask when you buy and for the bid when you sell. Okay? So if you have any questions about the setup, please go ahead and ask. This is a good time. No.
So the one
yes?
should be ST bar, the last question, at least this point. So.
No. This we keep the same S for both up and down, because here...
ST bar. You have to choose one.
Yeah, okay, yes. We are using, here I just called it ST to be non-committal, but we can call it ST bar up, okay? Because by definition they are the same, okay? Yes, so here you pick whichever you want, but whichever you pick here, you also have to put here, okay? While here you have to put them separately. Okay. Now, at this point, we want to write the Hamilton-Jacobi equation. We want to solve this problem. So, this already tells you that a problem with transaction costs, but with constant investment opportunities, is in some sense like a problem without transaction costs, but with non-constant investment opportunities. Why? Well, philosophically, here you can see why. Because we have an extra state variable, which is the portfolio composition. The portfolio composition, when you are in a frictionless market, doesn't matter. Because if you don't like your portfolio, you adjust it instantly to whatever you like, and you don't pay anything to go from one portfolio to another. Okay? That's what frictionless means. But here, that's not the case. If you have 40% in stock, and you wish you were 45% in stock, well, of course you can do that. You can go 45% in stock, but this is going to cost you money. So when you go from 40 to 45, your wealth will go down. So you cannot go from 40 to 45 while keeping your wealth constant, which is what was happening in a frictionless market. And that means that you have to keep track of one additional state variable, which is the amount of money that you have, for example, in stock. If you tell me the amount of money you have in stock, I tell you immediately how much you have in cash and vice versa. So you can either choose to track the total wealth and the amount you have in either cash and stock, or you can track the wealth you have in cash and the wealth you have in stock and call these two your state variables. And this is what I'm going to do. Okay? I'm going to call X the amount of money you have in cash at time t, and by Y the amount of money you have in stock at time t. So when you look at Ito's formula for this candidate value function in conjunction with the self-financing conditions we have written here, okay, what you're getting is this expression. Now, what is interesting about this expression is that there are not two types of terms. Typically, you have a drift and a diffusion term. Here you get also some new animal, and the new animal, actually two new animals, but of the same type. It's the p phi up and the p phi down, and the d phi down. So what are these? Well, a priori they could be drift. They certainly cannot be diffusions because they are supposed to be finite variation. Okay? But they also could be increasing functions which are not drifts. Okay? So they do not have to be absolutely continuous. Maybe they will be if the optimal strategy is absolutely continuous. Maybe they will not be. In fact, by Murphy's law again, they will not be. Okay? So these are going to be steeper than drifts, but less steep than diffusions. So they are in another category. They are like local time type terms. Now, what is the dynamic programming principle that we should use when we want to write the Hamilton-Jacobi-Bellman equation? Okay? So notice I'm not saying theorem, I'm just saying principle. It's like a meta theorem. It's something that you hope is going to be true and will lead you to the right equation, and then when you get the right equation, you will prove a verification theorem. So the idea is that the value function should always be a supermartingale, okay? No matter what you do, it will be a supermartingale. But if you do the right thing, it should also become a martingale, okay? That's the philosophical principle of optimal control. So if we want this to be a supermartingale, what does that mean? Well, this one we're going to hope that is going to be a supermartingale automatically, so we don't worry about this. The drift, well, the drift cannot be more than 0, right? If the drift is more than 0, we're in trouble. So the drift should be less than or equal than 0, no matter what. What about these terms? Well, phi up is increasing, phi down is also increasing, so the coefficients should be also less than or equal than 0. Okay? So this coefficient should be less than or equal than 0, and this coefficient should be less than or equal than 0. You can write them together in on a chain of two inequalities, that Vx over Vy should be between 1 minus epsilon and 1 over 1 minus epsilon. Okay? Now, that's the supermartingale condition on the two new terms. On the old term, we know that when these two are both satisfied, so suppose that this is satisfied, then this should be less than or equal than 0. So we have this equation here, which is the drift equal to 0. Okay. So what is happening here exactly? We have that the marginal value of €1 in cash divided by the marginal value of €1 in stock should be always around 1. Okay? So suppose that you have no frictions. If there are no frictions, to have €1 more in cash or to have €1 more in stock is the same thing, because you can always move them around. Okay? If you have transaction costs, then they are not exactly the same, because if you wish, you had more stock, 1 extra euro in stock is worth more than 1 extra euro in cash, because if you give me 1 extra euro in cash, I can turn this only in 1 minus epsilon euro in stocks, okay? So if I prefer to have more stocks, then I value stock more. If I prefer to have more cash, I value cash more. That's the intuition. So this ratio will be between 1 over epsilon and 1 over 1 over epsilon. When it is already, what you want is the old-fashioned HJB equation. Okay? But this is an HJB equation in which there is no soup. Okay? Why there is no soup? Because when you are here, it means that if you buy, what you gain by buying is less than what you lose by trading. And when you sell, what you gain by selling in terms of having a better portfolio, a portfolio that is closer to your ideal, is less than what you're losing by trading again. So this is essentially what is known as the no-trade region. In other words, here, this increasing function can be strictly increasing or can also be flat. This strictly function can also be either strictly increasing or flat. When this is strictly increasing, it means that you're buying. When this is strictly increasing, it means that you're selling. And if this is strictly increasing, this should be strictly less than 0, because it means that by increasing, then, when this is strictly increasing, this should be 0, okay? Because it means that the marginal value function is equal, that the marginal value of cash is exactly equal to the marginal value of buying, okay? And that's exactly the condition.
Is there anything which I hadn't seen yet, where it is forbidden, that, which of course doesn't make sense, but for the moment that they are both increasing?
No, if they are both increasing, it means that this is equal to this, but is also equal to this.
Okay.
So it cannot happen.
Oh, okay.
Okay,
so this is excluded.
Yeah, because if you buy,
As it should.
yeah, exactly. So, yeah, epsilon has to be strictly greater than 0, let's say. Okay. Otherwise, it doesn't matter. Okay. When you are in the middle, it means that it is optimal to do nothing. So, phi hat is flat, phi up is flat, and phi down is also flat. So here, the HJB equation actually becomes linear because you do not maximize over the strategy. Doing nothing is already optimal. Okay? And when the strategy is constant, by definition, the operator that comes from the HJB equation is already linear. Okay? That's the interpretation of this. Now, what we want to do is to solve this equation. In particular, we want to find V, and we want to find when this is happening and when this is happening. Okay? So how do we do this? We start using the wisdom we have accumulated from the previous problems, and we start factoring out the dependence on one of the two wealth variables. In this case, for example, we can factor out the dependence on cash. Okay? So the idea is that the only state variable that matters in this problem is the ratio between stock and cash. Okay? And after you tell me that, then if I tell you what is your cash, you should be able to find your value function given your eyes. Okay? So we're going to take this guess for the value function. We're going to plug it into the Hamilton-Jacobi-Bellman equation, and we're going to call the ratio between stock and cash Z. And this is what we're getting. We get this simple ODE for V, okay? And this chain of two inequalities becomes this relation between V prime and V and Z itself, okay? So, let's look at what we have here. So, we have an ODE plus an unknown parameter beta, which is the certainty equivalent rate on top of the risk-free asset. And then we also have to find what are the values of Z at which this is equal, and the other value of Z at which this is equal. So practically we have a second order ODE on an unknown interval, otherwise known as a free boundary problem. Okay? So, first of all, we guess that this is an interval. A priori we don't know, but I mean, it's not hard to guess from what we have discussed so far about the problem. So we're going to guess that Z has to live in an interval, L and U, L as low, U as up, lower and upper. So the free boundary problem looks like this. We want this ODE to be satisfied. We want on the left this equality to hold, on the right this other equality to hold. Okay? Now notice that this is hopeless if we write it like this. You just do some accounting. This is a second order ODE. It comes with two free constants, even if you write the general solution. So now you have two constants to find. Then beta is another constant you have to find. Three unknowns. Then let's not forget that we have to find L and U. 5 unknowns. How many equations have we got? 2. Something wrong. Okay? And what is wrong is that here we can solve this system, in fact, for any choice of L and U. So this Hamilton-Jacobi-Riemann equation, as it is, does not identify L and U. We have to find L and U with some additional conditions that are not in the problem so far. So what are these conditions? These are known as the smooth pasting conditions. So what does it mean, smooth pasting? It means that when you are at a boundary, such as L or U, the equation should still hold. Okay? So you should not have that there is a kink, but that the equation itself doesn't hold only on the open set, but even on the boundaries themselves. Okay? So practically, the way that you derive these smooth pasting conditions is that you look at your boundary conditions and you take the derivative with respect to the boundary itself. Okay? So you take the derivative here with respect to L, here with respect to U. And you ask these to be two extra conditions to hold for your solution. So now we are in better shape because we have 5 unknowns and 4 equations. But we still have one left. What is the problem with the other one? Okay, how do we find an extra condition? The idea is that it doesn't matter. Okay? Let me explain more explicitly. So suppose that here you have a solution V. Oops. And suppose that now I multiply this solution V by 5. Okay? Is the objective function going to change? Nope, because if you multiply this by a constant, when you take the log and you divide by t, it disappears. So we're not going to worry about that. We're going to find the solution up to a multiplicative constant, and when we do that, we have all the accounting in order, because we have 5 unknowns and 5 equations, essentially. The 5th one is arbitrary. You can decide that V of lambda, or V of L is 1, for So if we do some little algebra, we find immediately what are L and what are U. And actually, we're not going to focus on L and U themselves, but we're going to focus on this pi minus, which is L divided by L plus 1 plus epsilon, and on U, which is U divided by U plus 1 over 1 minus epsilon. So what are these pi plus and pi minuses? Pi minus is the proportion of wealth at which you sell, evaluated using the price at which you sell. Okay? Pi plus is the proportion of wealth at which you buy, evaluated using the price at which you buy. Okay? So these two quantities are important because they underlie the definition of shadow price. Okay? The shadow price is a hypothetical frictionless price for which the solution of the portfolio optimization problem would be the same as the without transaction cost as the solution to the original problem with the original price but with the transaction cost. Okay? So what is nice about pi minus and pi plus is that they have much simpler expressions than L and U. And in fact, they have these two expressions, okay, which tell you immediately what is going on. So what is going on is that the price at which you buy is going to be the Merton fraction plus a certain amount. Okay? The certain amount depends on beta, which we haven't found exactly. The price at which you sell, pi minus, is going to be, again, the Merton fraction minus the same amount. So you have opened a wedge around Merton, symmetric wedge, and you're going to sell when you reach the upper level. You're going to buy when you reach the lower level, and the two levels are symmetric around Merton. Okay? So if you want to be more precise, you can write this beta as the frictional values minus lambda, and then it becomes a simpler formula, but this doesn't really matter, okay? It's just what I said. Okay. So how do we find lambda, or beta, which is the same, okay? This is the only thing that we haven't done yet. So to do this, we need to use a little bit of algebra. So we're going to write V, which is the reduced value function. So it is the value function as a function of the portfolio decomposition, y over z, y over x, sorry. And we're going to say that this is going to be the exponential of the power of the utility times the integral of something, okay? And this something is what we're going to call our new value function. So we're going to make a substitution here. When we do the substitution, we are trading a second order ODE that was linear for a first order ODE that is nonlinear, except for log utility, which is always easier, right? So is this a good deal? Well, let's see. Well, the advantage of this substitution is that now the lower boundary is no longer a free boundary. This is 0, okay? The upper boundary is still free, okay? But at least now we have a Cauchy problem that we can only start at 0. Okay? So we can say, what is the solution of this ODE started at 0? Okay? And of course, the solution to this ODE will depend on lambda. Okay? So we can try for different lambdas the solution for this ODE. And then we want that the right lambda also satisfies this boundary condition. And this is how we identify the lambda. Okay? And this, you can also implement this numerically. It's not very difficult. But in fact, you can do even better. Well, I don't know if it's better, but you can be even more explicit, let's say. You can solve this asymptotically. So you can ask yourself, if my transaction costs are small enough, and usually they are small, okay? They will be, for most stocks these days, probably 0.1% or lower. Can I find an expansion of lambda? Because this solution will not be very explicit, okay? This ODE, actually, you can solve explicitly. It's a Riccati type of ODE. When you solve it explicitly, you will get some function of lambda, but when you match this boundary condition, you will get some transcendental equation which you cannot solve explicitly. Okay. So what you can do is to find a power expansion of W around 0 in terms of powers of epsilon to the 1/3. Why does epsilon to the 1/3 come out rather than epsilon to the 1/2? Well, that's because essentially the price that you pay for being away from Merton is of the order of epsilon squared. The price that you pay when you trade is of the order of 1/epsilon. And if you maximize function, a weighted average of this, essentially A epsilon squared plus B of 1/epsilon, and you find the optimal epsilon, it is always of the order of 1/3. Okay? But this is a heuristic argument that doesn't really matter here. At the algebraic level, you can just check that this is the case. So what I want to show you now is not the details of the asymptotic expansions, but how do you do the verification for this? Because everything that I showed you so far is totally heuristic, okay? So it doesn't come with any verification theorem. How do we do the verification? Well, to do the verification, we construct the shadow price explicitly. So what's the idea of the shadow price? Shadow price is a hypothetical, okay? It is an asset that does not exist in reality. But that, if it existed, it would have a price, S tilde, which is always between the bid and the ask, okay? So if I ask you, do you prefer to trade the original asset, which when you buy, you pay the ask, and when you sell, you pay the bid, you get the bid? Or do you prefer to trade the shadow price? The answer is the shadow price, because when you pay less. When you get paid more, okay? So the shadow price is always better. Now, suppose that I tell you that there is a strategy which is optimal for the shadow price, and that the same strategy gives you the same payoff both for the shadow price and for the original price. Then you tell me, well, then this strategy must be optimal also for the original price, because it does a job that is as good as it could be even for the shadow price, okay? This is already optimal for the shadow price, okay? I cannot do anything better with the original price, okay? Essentially, you have two functions. One is always above the other, okay? And if you know that the one that is below touches the one that is above at the point where the one that is above reaches its maximum, then you know that this is also the maximum for the function below, okay? So it's a very simple argument once you write it in terms of function. So this is what we're going to do. The difficulty, of course, is that you have to construct such a price, because nobody says that there is a shadow price, okay? So if you can exhibit it, then you can do it. And the idea is that you do exhibit it by working with the value function that you have constructed, okay? So you're going to guess that the shadow price is going to be proportional to your price times a certain function that here it is convenient to write as g of e to the y divided by e to the y. Okay? And then you want that this function is a nice shadow price. Okay. So what do we have to require for this function g? Well, the function g, let's talk about g of x over x. G of x over x must be always between 1 minus epsilon and 1, okay? Otherwise, this is not a shadow price. Also, it will have the property that when it reaches 1, okay, the diffusion term must be 0. Because if it reaches 1 and the diffusion term is not 0, it will breach 1 immediately. Because diffusions, you know, are restless. They will breach whatever point they are in both directions in no time. Okay? So the diffusion of g of e to the y divided by e to the y must be 0 at level 1, and it must be 0 also at level 1 minus epsilon. And when you write these two conditions, you get these two pairs of equations, okay? So g of 1 must be this, and the g prime of 1 must be this, which is the diffusion condition, okay? And the same goes for the other boundary, okay? Now, okay. Yeah, that's what I said. So now you take the dynamics of S tilde, and you want to see what it looks like. Now, the dynamics of S tilde, the shadow price, is not going to be a Merton dynamics. It will be close to the Merton dynamics, but not quite the same. In particular, the drift will be non-constant, and the volatility will not be constant as well. Okay? But you can write this, again, as a function of our state variable y. So you see that now we have gone from a market that had constant opportunities and transaction cost to a market which has time-varying opportunities, but no transaction cost. And the two are going to be the same. Okay. So in this market, now we can solve the optimal investment problem without transaction costs. Okay? We can write an HJB equation, as we did earlier. So if we write the HJB equation for this market, we get this expression. I'm not going to go through all the steps again. It is exactly what we did yesterday. And now the HJB equation for this one is that this soup of the drift should be 0, as it happens in regular HJB equation for frictional markets. And what are the boundary conditions we get for the state variable? Well, here we have to worry about the state variables because the state variable is not as it was in the previous discussion. Now here it is a reflected diffusion. It is a Brownian motion that lives in an interval and that is bouncing off its. So we need to write the boundary conditions. Well, what are the boundary conditions? We write the Neumann boundary conditions that the value function should have 0 derivative when you touch the boundary. Why 0 derivative? Because that's the only way that we are going to get a martingale for the value function. Okay? Otherwise, the drift is not going to be 0. Because there is going to be some drift coming from the state variable, and if I know that I'm at the top, I know that I can only go down, so the drift will be negative. And if I know that I'm the bottom, I know that I can only go up. So the coefficient when you are at the top must be 0, and the coefficient when you are at the top or the bottom must also be 0. That's the only way that I don't know where my V is moving. Okay? And that's the martingale condition. Okay. So if we write it like this, we get the optimal portfolio, which is given by this expression. Okay? And if you plug the equality back in the HJB equation, now you get this more complicated HJB equation. And the certain equivalent rate is going to be this expression. Okay? Now, this is just algebra. There is nothing particularly deep. It's just a calculation. You do another substitution, similar to the one we did before, and you get this other Riccati equation, which looks very similar to the one we had earlier. Okay? And again, here, the Neumann condition gives us these two boundary conditions that are inherited by what we wrote in the earlier slide. Okay. Now we have an HJB equation for the market with transaction cost, and we have an HJB equation for the shadow market. If they are the same market, the HJB equation better be the same. Okay? So now we are going to say we want them to be the same. And when we say we want them to be the same, we find what is our unknown function g, which we had written originally to describe the shadow market. Okay? So this is a bit complicated, but it tells you exactly what is g from this equation here. Okay? Okay. So I realize that this is a bit messy. It is what it is, and just want to give you the idea of how this proceeds. So when we set that these two equations are the same, and we do the simplifications, we get that this expression, that this square, should be equal to 0. So if the square is equal to 0, the argument of the square is equal to 0. And now we get an ODE for G in terms of W. Okay? You do one more substitution, and you find this ODE to be linear. Okay? This, you know, you have to like ODEs when you do these things, otherwise it's a lost button. Okay? And finally, you find the expression for the value function W, okay? Which can be written like this, in terms of lambda, of course. And then you have to find the value of kappa. From the value of kappa, you find the value of G. And G gives you exactly the expression for the shadow price, which is not pleasant, but it is explicit. Okay? Now you have the shadow price, and you can do the verification. The way you do the verification is that you do the exact finite horizon bounds that I showed you in the previous lecture. You could say, no, you can't, because your diffusion does not live in an open set. And I reply, yes, I can, because I have set the boundary conditions to be Neumann, and therefore I can repeat the entire steps without any problems at the boundary, because we have Neumann conditions. Okay? So I'm not going to give you the details of those calculations because they are not important. What is important is that now you have a finite horizon upper bound for the shadow price. The Q that you get in this particular problem is actually bounded. So you don't even have to estimate anything here. You know that this is bounded by m. When you take the log of m, you divide by t, goes to 0, hands down. Okay? Now, the expression for the myopia probability, we don't really care. And I'm not going to discuss the bounds. I just want to tell you a little bit about the interpretation of the result. So in particular, what is the certainty equivalent rate? Well, certainty equivalent rate if we didn't have transaction cost, would be this. Okay? We have found this expression already. Transaction costs are going to reduce a little bit this certain equivalent rate because trading in a market with transaction cost is just worse than trading in a market with, without transaction cost. So how bad is it? Let's just skip this. If you want to see how bad it is, you have to look at the expansion for lambda. Okay? And the expansion for lambda is of the order of epsilon to the 1/3, as I mentioned earlier, plus some other term, which is actually of order epsilon, not epsilon to the 2/3. So the next term is actually 0, which means that the first order approximation is even better than it should. So the certain equivalent rate at the first order looks like this. And when you look at this expression, you see that it makes a lot of sense. Because suppose that your optimal strategy, under Merton, let's say, is to be 100% in the risky asset. Okay? So then, how much do you trade? 0. You just get 100% of the risky asset. If you're 100% today, the market can do whatever it wants. You will be 100% tomorrow. In fact, the effective transaction cost here is 0 when pi is equal to 1. If your optimal strategy is to stay out of the market, pi equals 0, likewise, you're not going to trade. You don't care about transaction cost. When is that transaction costs have the largest effect? When the volatility of your portfolio itself is highest. And that's actually when you are either at 1/2, if you are just confining yourself between 0 and 1, or much more seriously, when you are either short or leveraged. Okay? So if you look at what is happening when pi becomes really large, for example, when gamma is really low, then you will want to be leveraged, so pi will be above 1. And if pi is above 1, you see that this is rising quite quickly. In fact, it is of the order of pi squared. Okay? So the more leveraged you are, the more you're going to trade. The more you trade, the more transaction costs are going to hurt you. Okay? This is what this is telling you. It is also telling you that the bigger the volatility, other things equal, the worse the effect of transaction cost, because the volatility moves around the portfolio, and that's bad because you would like the portfolio to stay as constant as possible in a Merton world. Okay? Now, if you look at the trading boundaries, everything that I told you earlier for the certain equivalent rate basically carries over. So the trading boundaries are opening up around Merton by an amount that is larger when the effect of the transaction cost is larger, and by an amount that is smaller when the effect of the transaction cost is smaller. So when transaction costs are really bad, you try to become more tolerant in your portfolio. When they are not so bad, then you can be more picky. Okay? That's what this expression is telling you. And if you want to study also trading volume implied by this rebalancing policy, here you can do it. You can look at, for example, the number of shares that you trade. This would be the variation of phi divided the absolute number of shares that you have right now. This quantity is also ergodic. You can estimate it asymptotically, and you get an expression that qualitatively looks like the ones we had earlier, but here you have a different weight for the pi star and 1 minus pi star parameters. And that pretty much concludes what I wanted to tell you, and I thank you for your attention. Questions?
said that this is an asymptotic estimation and
Yeah.
an asymptotic building of the portfolio. So even for the no trading bounds,
Yes.
okay, you have. Can you give an intuition how this trading bound changes when we approach it to the horizon?
It becomes larger.
Yes, but according to what order of T, capital T minus T?
You want to know the order as a function of the time to
Yes.
maturity? I don't know about that. Actually, there's a paper by Liu and Lowenstein where they solve that problem, but I don't know whether they have this order. But so I know that this is self-serving, but to some extent it doesn't really matter because the effect is really, really small. So when we looked at defined horizon bounds for this problem, we saw that if your horizon is more than 1.5 years, practically, even if the transaction costs were 1%, the long-run solution will be already almost indistinguishable from the optimal one. So unless you're talking about really illiquid assets like 10%, 5% transaction cost, then it becomes relevant. For most assets, it doesn't matter so much. Anyway, the short answer is that I don't know. I'm not even sure whether this is of power type, right? But I mean, one quick and dirty way to try to find out is probably to use exponentially distributed horizon, which is easier to deal with. And then you look at the rate, the arrival rate of the horizon to go to plus infinity, and then you try to get an expansion in terms of this rate. And then one of that rate is the average horizon anyway. That might be a way to do it tactically. Okay?
Okay, thank you.
Thank you.